Good morning, game theorists, or good afternoon, or good night, depending upon whenever you're watching this. Today we are in chapter 17, looking at the very final section, which is about alternating offers with impatience. As in our previous episode, the two sides will take turns making offers. Perhaps person A offers in the first round. If that's rejected, then B makes an offer in round 2. If that's rejected, then A offers again in round 3, and so on. The difference here is that instead of subtracting off a delta every time no deal is reached, now we're going to multiply by a delta. The delta is going to be something less than 1. So one big difference here is that each player can have a different delta. So the players might not be equally desperate to reach a deal. So, as always, our original surplus is going to be the value of what's at stake minus each side's BATNAs. Parent BATNA is the best alternative to a negotiated agreement. This is what you get if no deal is reached. I used the example earlier where when I was negotiating with Binghamton for this job, my BATNA was the salary I could have gotten by staying at Truman State University, where I was working before in Missouri. So the amount of value net of the BATNAs is the surplus, the gains from working together. I guess it's to say, should say that delta A is also bigger than 0, so it's positive. So if there are 2 rounds where you have no deal, then that's going to be delta squared A. If it goes on to a 3rd round with no deal, that becomes delta cubed, and so on. So why might the two sides be unequally impatient? It's not too hard to see why that could be true. So, for example, you could be looking at negotiations between a company and a union. If the company has a lot of cash on hand and the workers don't, then what's going to happen? The workers are going to want a deal really, really fast because they are going to burn through their savings quickly. The company's got money, they are not in a hurry. So in that case, you would want to care about the deltas being different, and this would be the appropriate way to model it. Now, back earlier we talked about present value. We used deltas for that as well. One motivation for present value was it's not just about impatience. It was rather that you have this opportunity cost if you receive money in the future rather than today. If I get money today, I can invest it right away and start earning interest. If my money does not arrive until the future, I can't invest it until later, so I miss out on some of that interest. You can use a similar story to motivate this section. So the opportunity cost these two sides face is what interest they could earn on their investments. Maybe A has different investments than B does, and maybe the rates of return are different. That's going to imply different deltas. So that's how you set up the story. Now, how we solve this model is actually, I was a bit surprised by how straightforward it was. So we had to define a bit more notation. So we'll define SA to be the amount that player A can guarantee themselves in the next round. Hang on a moment. I gotta make sure, is this the amount total for A or is this the amount of the surplus? It's the amount of the surplus. Similarly, SB is the amount of surplus that player B can guarantee themselves. So because this happens in the future, the value today of SA is going to be delta A SA. So you discount the future, just like we said earlier when we talked about repeated games. It's better to get the money up front because if you do, you can invest it and earn interest. If you have to wait another period to get this, it's less appealing. And likewise for player B. So they can get SB next round. Today, however, that's only worth delta B SB, which is a little bit less than SB. So here's how we can solve it. So SA is going to be the share that A can guarantee themselves is you have the initial surplus, B minus A minus B, but then you have to offer B what they can guarantee themselves next round. Same kind of logic we saw in the earlier episodes. If I can guarantee myself at least 10 in the next round, you have to offer me at least 10 right now to get me to accept. Now, because that happens in the future, it gets discounted. So if B can get $10 tomorrow, that's not the same as getting $10 today. Maybe $10 tomorrow is only worth $9 today. So while they can get $10 by saying no and going to another round of negotiations, they'd rather get $9 today because they're impatient. So you can offer them $9 today and they'll still say yes. Now, player B's got to think about if this goes on one round longer and I'm making the negotiations, what would I offer and what can I secure for myself? Well, there's going to be that initial surplus, but I got to offer A what they can guarantee themselves. But A is impatient, so I can discount that by delta A. Same logic. So even if A can guarantee themselves $10 next round, because they're impatient, they'd rather have $9 today. Therefore, I can offer them $9 today. They'll still say yes, even though they could get $10 next period. So with this setup, you'll notice we have two equations and we have two unknowns. We're trying to solve for SA and SB. In a problem, you'll be given V, A, and B, and also you'll be given the deltas. So you have to know how impatient the players are. So let's see, how should I tackle this one? Let's just sub out SB. So SB is that. Let's expand. I guess I don't really need these parentheses. So that's delta B times V. Here we have 2 minus to make a plus, so that's going to be delta B times A. And same thing, 2 minus to make a plus, delta B times B. And I get a plus delta B, delta A, SA. So let's move this guy to the other side. So I have all my SAs on one side and all my other stuff on the other side. And I can start combining these guys. So this becomes 1 minus delta B times V minus A minus B. And now I can factor out the SA over here. And very last step, to get SA by itself, or in these times, I like to say to quarantine the SA, we divide both sides by 1 minus delta A minus delta A delta B. So that gives us that SA is 1 minus delta B times initial surplus divided by 1 minus delta A delta B. And by symmetry, we get that SB is 1 minus delta A times initial surplus over 1 minus the deltas. So let's head off one possible misconception here. It might be troubling if you notice that if you add these together, they're going to sum to something greater than 1. Or to say the sum of SA and SB is greater than the initial surplus. So what could be troubling is that if you're only dividing up, say, $10 of surplus, you can't divide up $11 in total. There's only $10 there. But remember, you don't offer the other person their S, you offer them the present value of their S. So if you're person A and you get to make the first offer, here's what you do. You keep SA for yourself, SA given by this formula, and you offer them the present value of SB. So that'd be delta B, SB. This is how you divide up the surplus. Similarly, if B makes the first offer, then they take SB for themselves, and you offer not SA, but the present value of SA, instead. So, as I was saying earlier, a couple of things. So first I mentioned there is an advantage to offering first. Because the surplus is diminishing, that gives each side a strong incentive to reach an agreement quickly. Because they're desperate to get a deal, if you offer first, you can bias the deal in your favor, and they'll still say yes, as long as you don't bias it too much. So that's one observation we made earlier. This is how you divide up the surplus. Be careful about, we're talking about the surplus, we're talking about the total amount that they get. So the surplus is what's at stake net of the BATNAs. We said earlier, though, you have to give each side at least their BATNA to make sure they say yes. So in this case, A gets this of the surplus, and they also get their BATNA. B gets SB of the surplus, and B also gets their BATNA. So that concludes this episode. Be sure to tune in next time, and we'll learn some more.